Welcome everybody, welcome to our lecture, and today we will discuss Heapsort, and it is chapter 4. Okay, so in our textbook, if we go to chapter, actually the index, we have like 6, right? Page number 6 or 7. So the chapter 6 is about Heapsort, and then we will discuss 6.1 what is heap, and then 6.2 maintaining the heap property, 6.3 building a heap, and then we later we will see how to use these concepts in order to develop a heap sort algorithm. Okay, and the later we will discuss priority queue. Okay, so let's get started. And again, I'm using Dr. Lee's PowerPoint slide, so I would like to thank her again. Okay, so heap sorting algorithm. Okay, so it is another efficient sorting algorithm, although it is not well known, and so like people who usually use insertion sort or merge sort algorithm. So in our previous lecture we discussed that how to use merge sort and insertion sort algorithm, right? So actually the heap sort combines the advantages of both insertion sort and merge sort algorithm. Okay, so as we know that in the insertion sort algorithm has time complexity of big O n squared, but it is efficient when the array is almost sorted, right? And the merge sort algorithm, we learned that so merge sort algorithm has, in the worst case, it has time complexity n log n, lg means log in base 2. Okay, so and another thing is that so insertion sort is in place, okay, in place sorting algorithm, and so it does not need extra memory. But merge sort algorithm takes less time, although it is required that okay, so it is not in place. Okay, so let us open the book. If we go to the book, maybe 171 is number, because there are some index pages. So Heapsort, actually Heapsort, it combines the advantage from merge sort and insertion sort algorithm. So what are the advantages? Like one thing is that like merge sort, okay, but not like insertion sort, heap sort running times is n log n. This is an advantage. Okay, and the second is that like okay, maybe I can do this way. So one thing is that like merge sort, this is properties 1, advantage 1, like merge sort but not like insertion sort, heap sort running time is n log n, and number 2 is here like insertion sort but not like merge sort, heap sort is in place. Okay, so only a constant number, that means only a constant number of array elements are sorted outside the input array at a time, but most of the elements are sorted in place. Okay, so although the heap sort is unusual, and because we commonly use merge sort or insertion sort, but as we learned that heap sort has almost same time complexity like merge sort, and it has some extra advantages that we get in insertion sort. So let's start it. Yeah. So now what is a heap? Actually a heap, so in order to understand the heap sort algorithm, actually I'm sorry, So unlike insertion sort and merge sort algorithm, heap sort is unusual, but let us start and let us now learn something new. Okay, so first of all, what is a heap? Well, heap is a kind of binary array. Okay, so it's a binary tree. Okay, so it can be used to implement a priority key. We will discuss priority key later, but it is implemented as an array. Okay, so it is completely filled in, and it offers both insertion and deletion with big O log n. Okay, log n time. So you know that n is the number of elements. Okay, so in order to understand heap, we said that it is a completely filled in, right? Complete binary tree. Binary tree, as you know, that a tree that has only two sides, left and right, two children, left child and right child, right? So this is a complete tree, but complete binary tree, but this is not a complete binary tree. Okay, so the second one, right side one, is not complete binary tree. What is the reason? That it is this is missing over here, right? So it should be filled first. So this should be missing. Okay, so this element should go here, this element should go here, and this element should go here. Okay, so this is why it is not complete. It is not a complete. Okay, so then so this means that it means it's a completely filled in reading. It's reading from left to right. Okay, but sometime the last row may be incomplete. If the last row is incomplete, then it will be still completing from the left to right. Okay, so this one is it is complete. Okay, so a heap is a binary tree with these properties. First of all, it is a complete binary tree. Second, it is implemented as an array, and each node in the heap satisfies the heap condition. So what is heap condition? Heap condition is that if a parent key value, every parent has its value greater or equal is both of its children value, left child and right child. Okay, so that means here so 100. Okay, this is with index 0, so this is we can say it's root. The value must be greater than both left child value 90 and right child value 80. Okay, so then it maintains the heap property, but for all nodes this should be maintained. Okay, so 90, you see the 90, it is greater than 30 and 60. This 80, it is greater than 50 and 70. Okay, so this is the last one. Okay, so and the heap array, so this can be implemented in heap array. That so index 0 it says 100, and index 1 90, index 2 80, index 3, okay, index 3 is 30, index 4 is 60, and so on. Index 6 is 70. Okay, so this is the last element. Okay, so the book, actually, if you read the book, so there is a difference between our slides and the book, is that the book has an old school style pseudocode format. Actually, we know that in pseudocode we assign the index starting from 1, right? So this 16 has index 1, and then it is had index 2, it is index 3. But if I would rewrite this, so in a more recent programming languages format, so then I would say this is index 0, this is 1, this is 2, and 3, 4, 5, 6, like this way. Okay, and on the right side it shows that who is which elements are the children element of is root 16. Okay, 16 it has a child 14, another child is 10. Okay, you see that 16 has one child 14, another child is 10, and 10 has one child 9, another child is 3. So 10 has one child 9, another child 3. Okay, and okay, 14 has one child 8, another child 7. So 14 has one child 8, another child 7, and 8 has one child 2 and child 4, and so on. Okay, so but the main difference between the book and our slide is that book has discussed with index, starting with index 1, but in our slide we have discussed with index 0. Okay, that is for usual array that is used in most programming languages. Okay, and another thing is that how do we remove heap elements? Okay, so remove the node with the maximum key. Okay, so the maximum key will be the last one. Okay, this node is always the root. Okay, maximum key. Okay, maximum key will be the root element. Okay, so this root is always with index 0, so maximum key, so this is the with maximum value. Okay, maximum key value with the root. Okay, so later we will see that we will maintain this property throughout our Heapsort algorithm. Okay, so the problem is that once the root is gone, right? So for instance, in order to do when we remove this element from the binary tree, so this element is gone, right? So then what do we need to do? We need to complete this element. Okay, complete this element, because it cannot be empty, right? So then the question is that how do we fill out this element? Okay, we have multiple ways. For instance, we can think that we can move 90 over here or 80 over here, but in that case 90 or 80, these two child will be empty, right? One of these will be empty, right? So in that case this child need to be filled from their children, right? Okay, so then like more time will be needed, right? Here, so but in that case what we can do, think about, there is an efficient way there. How about if we move the last node to here? Okay, last node value from here to here, right? So then we know that last node value has index n-1, right? So that heap array, if we move the last element from the heap array with index n-1 to index 0, right? So then that means it will no longer be empty, right? So that this value will be moved over here. So now there is a problem here. What is the problem? So we see that when we already have moved the root element to somewhere, right? And now we are copying this last element to the root, right? So that means we are getting one extra element in our list, right? That means the last element is already here and it is moving a copy is here, right? So then what do we need to do? We need to remove the last element, right? So how can we remove the last element? So if we decrease the array length by 1, so that means this last element will be unlinked, right? This will not be linked anymore in our array, right? So this is the trick. Always say that this is the trick, that we move the last element to the root and we decrease the size of n by 1. Okay, so it shows that the last element is moved over here, this element was removed, then the last element will be moved over here. Okay, and now then when we last element we move the last element over here, so that definitely the last element so will not be the largest element, right? So in order to maintain a heap property, what we need to have the root element greater than both of its children, right? Left children and right children. So here we see the 30 is less than 82. Okay, and also 51. So but we will check first left element first. So then 30 will be swapped with this one. Now this by this swapping, okay, so 82 will come over here. Okay, so since we know that this left element will be greater or equal to right element, so then that means now 82 will come here, so then it is okay for this part, but 30 again will come here, right? So 13 again it will come here, so then 13 needs to be swapped, right? So either with with 63 left or right, right? It's 30 it needs to be swapped. Okay, and then so 30 is swapped with 70 for now, and then okay, so then and then again this 30 will be swapped with 55. Okay, so that means insertion uses some trickle up, okay, rather than trickle down of removal, that means removal. So initially the node to be inserted in place in the first open position at the end of the array, and then whenever we increase the array size, then we need to do this time we need to increase the n plus 1. So where is this one? This is heap array. Okay, so it is heap array. We are putting every node, taking one node from the heap, and we are putting in another array, and we are increasing that heap array size. Okay, but see that here one thing is that so we are decreasing over here to maintain to when we copy the last element. Okay, so now how do we insert a node in a heap? So inserting in a node in a heap, we know that will go initially, that will go to the last element, right? So here, so this is the 73, so 34 is the last element here, so that any new element will be in placed here this time first, right? So then this new element, so when what will happen, these two elements will be swapped. This needs to be will be checked with his parent, right? So parent value cannot be less than its child value, so the parent will go over here. Okay, so parent will go over here, then again this parent will be swapped over here, and then again this will be swapped over here, right? So okay, so that is the process of inserting in a heap. Now okay, so unlike the book, I see that in the book it has index started with index 1, but in our slide we have started with index 0. So a node position in a tree as an array for a node at index I. For instance, any node with index I can be 0 to any number, for instance 0 to 1 to 3. So parent index will be I minus 1 by 2. So if for instance I here, if I equal to if say I equal to so index start with 0, so 0 minus so I equal to 0. So then if index equal to whatever is index is I to equal to 1, so the parent index is I minus 1 by 2, and actually we need to take ceiling, okay, over here, ceiling floor, and the left child will be 2I plus 1. So actually I should be start 1 here or here, okay. So okay, no, I should start 0 over here. It will not go 0, and 2 is equal to 0 plus 1, this one will be 1, and this one 2 times 0, this one will be 2, right? Okay, so there is actually from the book, if I compare with the books, there is a difference between the book and our slide. Actually book, it has taken, since it started with the index 1, so it takes float, okay, for parent and then child, it takes 2I and 2I plus 1. So there is a difference between the book and the slide, okay. So please, okay, don't be misleaded. Okay, so this figure is from the book, okay. So book has index 1, so if index start with 1, so then this will return this, okay. But if we start index 0, then you will consider this. So started 1, so parent I equal to 1 by 2 is floor, since it is integer number, okay. So it will be taking 1 over here, okay. And then this is 2, I equal to 1, this is 2, and this is 2 plus 1 is 3, and so on. Okay, now heap has an important properties, okay. So what are the properties of heap? So heap also satisfy the heap property, okay. So what is heap property? A parent element is always greater or equal to its child element for all nodes, okay. In other words, the value of a node is at most the value of its parent, okay. So it's not at most, it is not at least, it is at most, okay. So be careful about this. So there will be some quiz questions related to from these slides, okay. So now the question is that what is the largest element in a heap sorted, okay. We're coming to that question soon, okay. So so that means in a heap, so then the parent element is greater or equal to is its child elements, right? Both child, left child and right child. In other words, the value of a node is at most the value of its parent. Thus the largest element in a max heap is stored at the roots, right? So where is the largest element stored? Because the largest element is stored at the root, because root has the highest or largest value, right? And the subtree rooted as a node contains the values no longer than it contains is it knows itself, because this property will be maintained for all over the binary tree. So for each part, so this is a completely binary tree, and we can say this is another subtree, this is another subtree. For each subtree, okay, the root element is greater or equal to the child element, okay. Left child element and right child element, or all children element. So what is the last value? Maximum value is stored as a root. Okay, now in order to understand the another thing is that important property, that heap height. So what is the heap height? Okay, so for instance, this is one thing is that length. If we say heap is stored in an array, So the length is n minus length is n, right? And what is height? Height, that means whenever it is organized as a binary tree, right? So this part has height 1, this part has height 2, and this part has height 3, right? So that means we can see that if it has at least one value in the last row, right? This is the last leaf. So then what is the height? Is it increasing log n by log n, right? Every time it is dividing by 2, so then height is increased by log n, right? So that means the height of a node of a tree is the number of edges on the longest downward path to a leaf. That is what means actually the height is the longest. Okay, it's the longest. Actually, if it has only even if it has at least one element in the last leaf, then we have to consider that. So that's here 1, 2, and 3. Okay. So so height of a tree equal to the height of its root, okay, not its child. Okay, and how do we find the height? It is a binary tree, so we can say log n. LG means log with base n. Okay, so this is an important property that we will see that we will need this. Okay, when we do our heap sort implementation. Okay, now how do we maintain the heap property? Okay, so now I think we can scroll this book, so I like you to read the book also. Okay, so actually there are two kinds of heap. It's called max heap and min heap. Max heap is used for implementing heap sort, but is min actually max there is another one, it's called min heap. We're not discussing that in here. Okay, so when you read this chapter, I will give you some assignment question from the book exercise mainly. Okay, from the book exercise. Okay, so maintaining heap property, so we need to so what are the heap property? Heap main property is that the root element must be greater or equal to its children elements, right? So in order to implement a heap sort algorithm, we need to maintain that property. So in the book, and people say that is called max Heapify. Okay, so max Heapify, that this algorithm, this process is ensures that the heap always maintains its property. Okay, so this is the algorithm. So and then just come to that algorithm. Okay, so these are the facts. For instance, there is given an array, an index I into the array. So given the max Heapify, assume that the binary tree rooted at left I and right I are the max heap. Okay, and the problem that okay, AI might be the smaller than its children, thus violating the max heap property, right? At any case, like we discussed that whenever we move we move the last element to the root, and that case it may happen that, or it actually happens that the root elements, it becomes smaller than its children, right? So then what do we need to do? We need to call the max then max Heapify algorithm to let the value at AI, that is the top element, okay, in the max heap, so that its substituted index I obey the max heap property. Then we need to actually solve. We need to do internal some swapping, so that it maintains the property that, what is the property, that the root index is greater or equal to the child index, child value. Okay, so this is the algorithm. Actually this is the from book. This algorithm is come from book. Okay, so what does it say? Let's see. So it says max happify is a method. Okay, and we will see that it will be a recursive method. Okay, so the recursive method will be coming here, it will call itself. Okay, that's here. So first of all, it's an array, it takes two elements, an array and an index I. Okay, so then initially let us state L equal to left index value, left key value actually of the index, and then R is right value. Then if L less or equal to A dot heap size, okay, and AL, okay, greater than AI, then we need to convert, we need to say A largest equal to L, otherwise largest equal to I, and then otherwise, so then if R, so for instance for the right element, okay, so if the right element is greater than, actually if this is the left, if this actually this says if the left element is greater than the root, then we need to consider the left as the left element is the largest. Otherwise, if the right element is greater than the root, then we need to consider the right element at the largest. Okay, and if largest not equal to I, that what we need to do, we need to exchange AI with a largest. So largest, what we consider over here, either the left child or right child, right? So then we need to we need to exchange those, right? It is a swapping over here, right? Exchange means swapping. Okay, and then what do we do? So then we need to call the max happify algorithm again with largest, to check the largest value is, to check this same process for the next sub tree. That means if we go, so for instance we need to check whether this value is greater than this value or this value. If one of these value is greater than this value, then we need to swap that again. Whenever this value will come over here, we need to check this one with this one and this one. So if that is greater than, then what we need to do, we need to swap this again. So this is the process over here. So exchange means over here is swapping. Okay, and then this max happify algorithm is called recursively, right? So this is a recursive process. Okay, so this shows, this slide it shows that how do we do happify. Okay, for instance let us see, for the first level it is fine, right? 16 is greater than both 4 and 10, right? But 4 is not greater than 14, right? So that is 14, we need to swap 4 and 14, right? We need to swap 4 and 14. So then again, right, is 4 is greater than 2, then it's fine, then we need to go right side, and then but consider right side, then 4 is less than 8, right? So then what we need to do, we need to swap 4 and 8, right? So then 4 come over here. So in that case, this is for this one is for this branch, for this one each elements it satisfy happify, right? Okay, okay, so now let us see what is the time complexity of merge sort algorithm? Actually, we need, if we analyze our Heapify algorithm, okay, so this algorithm is a recursive algorithm. So let us come in the book. So this algorithm is a recursive call algorithm, right? So that this is the these are shown in the slide over there. Okay, so as we see that, so this algorithm, since what it will do, it will every time it is convert, it is we are this is a binary tree, right? So then it is convert, it is splitting the array size by half. Okay, and one thing is that, another thing is that, if think about the worst case, for the worst case, if there is one element, at least one element in the last what is that called, last row, or say, for instance, if I do not have all this element, for instance, let us think that I do not have this. Okay, so then how many elements we have? 1 2 3 4 5 6 7, right? 1 2 3 4 5 6 7. So then its length is 2, right? Height is 2, right? Height is 2. So every time we are splitting n by 2, we are splitting n by 2, right? But think about situation if there is at least one element in the last it's called leaf level, right? So then we need to go another level, at least one more level, right? So this is why if you read the calculation, if you read the book, then it will say the children subtree have a size at most 2n by 2 by actually 2 by 3n, right? This is actually 2 by 3n, 2 by 3n, that means 2n by 3. Okay, in the worst case occur when the bottom leaf when the bottom leaf in the tree is exactly half full. Okay, exactly half full. So this is not half, this is bottom row is half full. Then the worst case, then we need to set to n by 3, the worst case. Okay, so then it fails in the master theorem. It is the Tn less or equal to 2 n by 3 plus theta n. Theta 1 is needed for swapping or exchanging, right? Okay, so from the master theorem we know that this fall in the second case in master theorem. So in the second case in master theorem, complexity is big O log n. Okay, its complexity is big O log n. So then if its complexity is big O log n, and then we need to do n iteration, right, for n elements. So the time complexity is total time complexity later with the heap sort algorithm will come n big O of n log n, that we'll see later. Okay, so okay, so we need another slide. So the next part will be building a heap, and then we will use the Heapify and building a heap algorithm to implement our Heapsort algorithm, okay, to complete our Heapsort algorithm. So actually I have reorganized we have reorganized the lecture slides so into two parts. So this into two lectures. So the lecture 5 end up here. So that then with the analyzation of Heapify. So if you see that the analyzation of Heapify in shortcut, if you read it through the book, okay, so the since so it will come up with a, so anything, so that is 2n by 3, it is actually 1.5n, right? So 0.669, right? Okay, so that is almost half, right? Almost actually, so 2n by 3, actually we could say it is log n, close to log n. So okay, the worst case, the Heapify has, max Heapify has, the running time is big O log n. Okay, so then okay, so then we will see how to develop a heap, okay, and actually max heap, and then to implement this Heapify and max heap algorithm in order to develop our Heapsort algorithm. Actually, let me do that in my next lecture. Okay, thank you for now.